In this video, we are talking about systems of linear equations. So in the previous videos, we went over the mathematical background to understand matrices and how systems of linear equations are represented. And here we're going to start our discussion of solving systems of linear equations. And in particular, we're going to focus on Kramers Rule and Gaussian Elimination. So systems of linear equations arise in many different engineering applications. So just to get kind of an idea of the motivation behind this work, we can look at a few different systems. So for example, in mechanics, you can have spring mass systems subject to some forces, and this results in a system of linear equations where we want to find the displacements in response to the applied force, knowing the stiffnesses in the system. Other applications are in the finite element method, in mechanics, or in structural analysis. In chemical processes, they arise. Or in thermodynamics, for example, if we want to find the temperature distribution across a plate, this results in a system of linear equations. And in electrical systems as well. So all of these types of systems across any engineering discipline, there are many applications and many situations where we end up with a system of linear equations that we want to solve for our unknowns. So in this section, we're going to go through some techniques that can be employed to do that. So given a system of linear equations, we aim to find the vector of our variables x that satisfies the expression ax equals b, where a is the matrix of coefficients, and b is the vector of constants as the output. So the two categories of methods for the solution of systems of equations are direct methods and iterative methods. So first we're going to consider direct methods, where the final solution is obtained at the end of a prescribed set of operations. So no iterations are performed. And just a note, in MATLAB you can use the function linsolve with inputs a and b, where a and b are the same definitions that we're using here. A is the matrix of coefficients and b is the constants on the right hand side of your equations. So we're going to talk about lots of different techniques, and you can compare your results with linsolve in MATLAB. So first we're going to talk about Kramers Rule. So Kramers Rule is one of the early methods to solve systems of linear equations of the form ax equals b. The method works well, however, it is inefficient when the number of equations is very large. So how it works is that each component, xi, in the solution is computed as shown here, which is the determinant of di divided by the determinant of a, where di is the matrix formed by replacing the ith column in a with a vector b, and then the det symbol here represents the determinant. So let's see how this works. So consider the system of equations ax equals b defined as shown here. So the first thing we want to do is to compute the determinant of a. So in this case, the determinant of a is equal to 5. And then we need to form the matrix. We need to form our D matrices. So first we'll form the matrix D1 by replacing the first column in A with our vector B. So you can see I have replaced the first column in A here with my vector b, as shown in red here. And then I find the determinant of my matrix D1, which is -5. Then I form the matrix D2 by replacing the second column in A with b, as shown here. And then I find the determinant of my matrix D2, which is equal to 0. And then I can compute the components of the unknown vector x, as x1 is the determinant of d1 divided by the determinant of a. So this was -5 over 5, so that means x1 is -1. Similarly, x2 is the determinant of d2 divided by the determinant of a, so this was 0 over 5, so x2 is equal to 0. So my result is that x is equal to -1 and 0, and you can plug this back into our original equation and verify that it works and we obtain the same value of b. Now let's try another example. Consider this linear system shown here is a 3 by 3 system. First thing we want to do, compute the determinant of A. So in this case, the determinant of A is -4. And then we need to form the matrices D1, D2, and D3 by replacing the ith column in A with B. And for each of these, we want to find the determinant. So D1 is shown here. So we replaced our first column in A with B. And the determinant of D1 is 20. So that means that xi, or x1, is the determinant of D1 divided by the determinant of A, which is -5. Then I find D2, and here I've replaced the second column in A with B. The determinant of D2 is 40, so that means x2 is going to be 40 over -4, which is -10. And then we find D3 by replacing the third column in A with B. We find the determinant of that is -28. And so x3 is going to be -28 divided by -4, which is +7. So next we want to consider Gaussian elimination. So to solve a system of linear equations of the form ax equals b, what we're doing mathematically is setting that x is equal to a inverse b. But in our numerical methods, no inverse is actually calculated. Instead, in a series of operations, we will transform the system until the solution just turns out. So the following 3 operations can be performed on a system of equations without affecting its solution. We can multiply or divide any equation by a constant. We can add or subtract any 2 equations. And we can rearrange the order of equations. So doing any of these things will not affect our system. And these operations will form the basis of our Gaussian elimination methods. So the first one that we're going to talk about is called naive Gaussian elimination. And it's a procedure in which the linear system of equations is manipulated such that the coefficients of the component xi are eliminated from equation I plus 1 to equation n. So basically, they're eliminated from all the columns below the column in question. So this transforms a full matrix A into an upper triangular matrix, which we can call U, using these row operations. And then, when we have our upper triangular matrix, it's possible to solve for xn using the last equation, because if you recall, in an upper triangular matrix, the bottom row only has one element. So our last equation, we can solve for xn directly, and then we can use backward substitution to find the remaining components. Because once the bottom row is found, then the second to last row only has one unknown, and so we can work our way back up to the top. So the whole procedure is divided into 2 steps, forward elimination and backward substitution. So forward elimination transforms our full matrix A into an upper triangular matrix using row operations. So if we've got this matrix and that representing our system of equations ax equals b, after forward elimination, we end up with an upper triangular matrix ux equals c. So it changes both the a and the c, or the a and the b become u and c. Then once we've got our upper triangular matrix, we use backward substitution, where x is simply calculated from the last element to the first without needing to invert u. So the last row or equation has only one unknown. So after solving for xn, then the second last equation again has only one unknown, and so on. So we just work our way backwards to the first equation. So let's look at an example. So consider the system of equations ax equals b defined as shown here. With forward elimination, we first eliminate the coefficient of x1 in equations 2 and 3. So we want to get rid of the coefficient here and here. And we can do that by taking first -1 times equation 1 plus equation 2, and that gives us the expressions here. And you can see that I'm eliminating this goes to 0, so I'm eliminating the coefficient in front of x1 in my second equation, and I end up with a 0 in that spot. Then we can take 1/2 times equation 1 plus equation 3. So that gives me the expression here, and you can see again this goes to 0. So we end up with a 0 for our coefficient of x1 in equation 3. And this is where our equations are at now. So now we can eliminate the coefficient of x2 from equation 3. So our x1 coefficients are gone, and now we move here, and we want to eliminate this coefficient. So we can do that by going -3 times equation 2 plus equation 3. So that gives us what we have shown here. And you can see this is going to go to 0. So we end up with a 0 for our coefficient of x2 in equation 3. And now from here, we can use backward substitution to solve the system, which becomes very simple. So we start from the last equation and work backwards. So from equation 3, we have that negative 2x3 is equal to 17. So that means x3 is equal to minus 8.5. And then from equation 2, we have that x2 plus 2 times x3 is equal to negative 2. And we substitute in our x3, and we get that x2 is equal to 15. So this goes in here. Then equation 1, we have that 2x1 plus 2x2 plus 2x3 is equal to 6. And we know already what x2 and x3 are, so we can plug those in, 15 and minus 8.5, and we can solve for x1 is negative 3.5. So this means our result x is equal to negative 3.5, 15, and negative 8.5. So let's we can talk about this in terms of the algorithm of the naive Gauss elimination method. So this was shown using the procedure with how you would solve the equations, but we can do this in matrix form using the naive Gauss elimination method, which basically following exactly those same steps. So we first start by forming the combined matrix with dimensions n by n plus 1 by combining our A and B into one matrix. So using the same equations in the preceding example, we've got our A and our B here, and we want to find our combined matrix A, B, and we sometimes put this line between them to show the division between my A and my B. But we want to put it all into one matrix. And then we perform the forward elimination steps. So the general formula for the forward elimination steps is shown here. So my Aij is equal to Aij minus Aik divided by Akk times Akj. And so we'll go through kind of how we step through this algorithm. So the main diagonal coefficients, Akk, is called the pivot element, and it's very important in this algorithm. And so if we recall our index notation, the first subindex stands for the row and the second stands for the column. So Aik are the elements of the pivot column and Akj are the elements of the pivot row. So those are here. So this is the pivot element. These are the elements of the pivot column, and these are the elements of the pivot row. And then this is the element in question that I am trying to update. Okay, so let's see how this works. So we want to use our pivot elements Akk to eliminate the components Aik, with I going from k plus 1 to n minus 1, and j going from k to n plus 1. So if we've got our matrix here, we start with k equals 1, so our pivot element is A11, as shown here. And our pivot row is the first row, so row 1. So what we want to do is eliminate the coefficient of x1 in row 2. So basically we want to get rid of this coefficient here, which is our A21. So what we're going to do is take row 2 is equal to row 2 minus A21 divided by my pivot element times my pivot row. So A21, again, is the coefficient of the element that we're trying to get rid of. So what we should end up with is this matrix here. So we'll see how this comes about. And as you can see, we've gotten rid of the coefficient. A21 is now 0. So we do, to get through the whole row, we need to loop over j. So this is j is equal to 1, j is equal to 2, j is equal to 3, and j is equal to 4. Is going to give us the new value of each of the elements in my row I. So I is equal to 2. So when j is equal to 1, again, recall I is equal to 2 and k is equal to 1. So we can plug in all of those values into our formula here. So A21 is equal to A21 minus A21 over A11 times A11. So again, we've got k is equal to 1, j is equal to 1, and I is equal to 2. So then we can just grab all of our values from our matrix and plug them in here. So A21 is going to be 2, so that's the value we're trying to get rid of, minus, again, A21 over A11. So 2 divided by our pivot element 2, and that is equal to 0. So that goes in this spot in our matrix here. And so the element that you're trying to get rid of should end up being 0 because that's what we're trying to do. So this makes sense that we end up with 0 here. Then we increment our j. So j is equal to 2. So now we're looking at A22. We need to find the new value of A22. So it was 3, and we need to find out that it's going to be 1. So A22 is going to be my old A22 minus A21 over A11 times A12. So we can plug in our values here. So A22 was 3 minus A21 was 2. So that's this one here, divided by A11, again, our pivot element, and multiplied by A12, which is the one above the one that we're interested in. So that's 2. So this, when we perform this calculation, we get 1. Then we increment our j. So now A23 is equal to A23 minus A21 over A11 times A13. So again, this is the element that we're trying to update. So its original value was 4 minus 2 over 2 times the thing above it, which is 2. So my new value is 2. And finally, j is equal to 4, so j goes to n plus 1 because we actually also need to update the values in our column that was b. So j goes from k to n plus 1. So when j is equal to 4, we got A24 is equal to A24 minus A21 over A11 times A14. So we're trying to update this element here. So originally it was 4, and now we're going to get negative 2. So A24 is equal to 4 minus 2 over 2 times 6, where 6 is the element above the one we're interested in, so we get negative 2. So now we've updated our whole matrix, basically performing this operation. Row 2 is equal to row 2 minus A21 over the pivot element times the pivot row. So this is our new form of our matrix. Now we want to increment, we've still got the same pivot, k is equal to 1, the same pivot row, but now we want to increment our I. So we want to deal with row 3 here. So row 3 is going to be equal to row 3 minus A31 over the pivot element times the pivot row. So we want to get rid of this value here. So we're going to end up with this matrix, and you can see that now we've got a 0 in that place. So we'll just go through this a little bit more quickly. So we start with j is equal to 1, and plug in, so with j equals 1, I equals 3, k is equal to 1. We plug in our indices in our formula, and then we plug in the values into our equation, and we see that A31 is equal to 0, as we expect, because that's the one we're trying to get rid of. When j is equal to 2, we end up with A32 is equal to 3, so that goes here. When j is equal to 3, we end up with A33 is equal to 4, so that goes here. And when j is equal to 4, we end up A34 is equal to 11. So that goes in here. So now we've eliminated everything, all the coefficients below our pivot element. So now we can increment our k. So here's our updated matrix. So now we increment our k, so k is equal to 2, so our pivot element becomes A22. And our pivot row is the second row. And then we start with I is equal to k plus 1. So we only need to eliminate the things below our pivot row. So basically what we want to do here is take row 3 is equal to row 3 minus A32 over the pivot element times the pivot row. So basically we're going to try and get rid of A32, which is this value here. We're going to end up with this matrix, and you can see that we've gotten rid of the coefficient A32, which is now 0. So I don't need to start with j equals 1 because that's already 0. So we can start with j equals 2. Sorry, it's already 0 here. So we start with j is equal to 2. So with j is equal to 2, A32 is equal to, we plug in our indices in our expression, and we see that A32 ends up being 0, which again is as expected because that's what we're trying to get rid of. Then J3, j is equal to 3, we get A33 is equal to negative 2, so that goes here. And then j is equal to 4, we get A34 is equal to 17, so that goes in here. And now we've gotten through all of our rows, we eliminated all of the elements below our pivot element, and now we're left with an upper triangular matrix that we can go ahead and solve. So after the forward elimination step, we have an upper triangular matrix U, and our problem is of the form Ux equals C. So you can see that this is an upper triangular matrix as shown here. So next we want to do the backward substitution. So the element xi, with I running backwards from n to 1, can be found using this equation here. So xi is 1 over aii times bi minus the sum from j equals I plus 1 to n times aij xj. So it's important to note here that we're using the b to represent the elements in this column, although they're not the original B elements. So they are the elements in my updated combined matrix. So we start with n is equal to, with I is equal to n. So in this case, I is equal to 3. And we can use this expression here. So x3 is going to be 1 over a33 times b3 minus the sum. J equals I plus 1, so that's 4, to n, which is 3 in this case. So the sum doesn't really come into play in the first equation. So x3 is just going to be 1 over minus 2 times 17. So this is my aii is minus 2, and my bi is 17. So that means x3 is equal to negative 8.5. And then I change my I by decreasing it by 1, so I is equal to 2. And I can use the expression here. So when I plug in my values into my indices into the expression, I get x2 is 1 over a22 times b2 minus a23x3. So this is my x2 is going to be 1 over a22, which is this value here, times b2, which is minus 2, minus a23, which is this, times x3. So then I need to use my x3 from here in this equation, and I get that x2 is equal to 15. And then I subtract 1 again from my I, so I is equal to 1, and I get what is shown here. So now my x1 is equal to 1 over a11, which is 2, times b1, which is 6, minus a12 times x2, so that's 2 times 15. So this is my a12, and then my x2 was here, plus a13 times x3. So this is my a13 and my x3. So that means that x1 is equal to negative 3.5. So I will post a MATLAB implementation as a demonstration of this on eClass, which prints out the intermediate steps. And so for this example, the intermediate steps are shown here. And you can see that we end up with the same result that we did using our equations the first time. So minus 3.5, 15, and minus 8.5. So this method we've been calling the naive Gauss elimination. And so the method that we're describing here is called naive for a couple of reasons. So the first is that it fails to find a solution if a pivot element or one of the diagonal elements is found to be 0. So for example, we can consider this linear system here. So this is a very simple system, and the solution you can easily see from inspection is that x1 equals x2 equals x3 is equal to 1. However, if we use our naive Gaussian elimination algorithm, it fails to find a solution because when the second row is used for elimination, the pivot element a22 is equal to 0. So an error is encountered because we're always dividing by our pivot element. So we're dividing by 0 and we get an error and we don't find the solution. So this problem can be solved by exchanging rows 2 and 3, which is called pivoting when you're exchanging any rows. So pivoting is beneficial not only when one of our pivot elements, AII, is equal to 0, but also when AII is very small. So when AII is very small, then A is said to be ill-conditioned and is susceptible to round-off errors. And we saw in the previous videos what it means when a matrix is ill-conditioned and what can happen. So it is a good idea to do this pivoting anytime, not just when your pivot element is equal to 0. So in general, the naive Gauss elimination algorithm can be augmented to be not so naive by always exchanging the current row with another row that has the maximum absolute value in the column below. So if you look at all of the columns below and you see which one has the biggest value in your pivot column, then you exchange the rows so that your pivot element is the maximum value. So then you don't run into these errors with ill conditioning or dividing by 0. So exchanging only the rows is called partial pivoting. It is possible to also exchange the columns if you wanted to find the largest element in both the row and the column, and this is called complete pivoting. However, the exchanging the columns is rarely used because switching the columns changes the order of the variables, which adds complexity to the program that is usually unjustified. This process is usually not needed, but it is possible. So the second reason that the procedure is called naive is that the method produces an upper triangular matrix that can easily be solved. But it's important to note that if the system is already a lower triangular matrix, then there's no need to employ the forward elimination procedure because we can simply use forward substitution to find our x1, x2 up to xn in that order. So for example, if you have this system here, we can easily determine that x1 equals 1, x2 equals minus 1, and x3 is equal to 1, going through basically forward substitution. But if we employ the naive Gauss elimination algorithm, it would conduct all of these steps to transform our matrix to an upper triangular matrix and then get the result from there. So another method that is rooted in Gauss elimination is called the Gauss-Jordan elimination method. So 2 steps are added to the previous algorithm to arrive at the Gauss-Jordan elimination algorithm. First, each pivot row is normalized by the pivot element. So we end up with 1s along the diagonal. And then second, the coefficients above the pivot element are also eliminated. So we don't just end up with a lower triangular matrix, we actually end up with a diagonal matrix. And so as a result, the backward substitution step is not needed because A ends up being the identity matrix. So, and we can just kind of see why the backward substitution part is not needed. So if A is a diagonal matrix, like this, we can directly find the values of xi. So xi would just be bi divided by aii. And if A is the identity matrix, as shown here, then our x values are just equal to our b values. So xi is equal to bi. So let's again consider our same system and go through the Gauss-Jordan elimination algorithm. So we start with our pivot element. And the first thing we do is normalize our pivot row by the pivot element. So row 1 is normalized by a11. So basically what we're doing is row 1 is equal to row 1 divided by 2. So that gives us the set of equations here. So you can see that now the coefficient of x1 in my first row is 1. Then row 1, or the pivot, is used to eliminate the coefficients of x1 in all of the rows below. So we want to get rid of this 2 here and this -1 here. So we can do that by going row 2 is equal to row 2 minus 2 times row 1, and row 3 is equal to row 3 minus -1 times row 1. So taking our, if you look back at the algorithm or the formulation for the Gauss elimination method, this here is the element that we want to get rid of, divided by our pivot element, which we have normalized to 1. And same here, so this is the element that we want to get rid of, divided by our pivot element, which in this case is 1. So this gives the set of equations shown here, and you can see that we've gotten rid of the coefficients of x1 in all of the rows below our first row. Now we move our pivot to the second row, so our pivot element is in the position 2, 2. Row 2 is already normalized, so we don't need to go through that procedure, but basically you would do the same thing, divide the whole row by if the coefficient was not 1, you would divide the whole row by the coefficient of x2. In this case, we can move on, so row 2, the pivot is then used to eliminate the coefficients of x2 in the row below. So we want to get rid of this 3 here, so we say row 3 is equal to row 3 minus 3 times row 2. And that gives the set of equations shown here, and you can see we've gotten rid of our 3. Now we also want to use the pivot in row 2 to eliminate the coefficients of x2 in the row above. So we want to get rid of this here, this element here. So now we do that by saying row 1 is equal to row 1 minus 1 times row 2. So 1 is the coefficient of the element we're interested in getting rid of, divided by 1, which is the coefficient of our pivot element, which of course we normalized, and times row 2. So this gets rid of the element, the coefficient of x2 in the rows above the pivot as well. So now we can increment and move our pivot to the third row. So we normalize row 3 to the pivot element a33. So row 3 is equal to row 3 divided by -2. This gives the equations shown here. So you can see now my row 3 has a coefficient of x3 is equal to 1. And then I use my row 3 to eliminate the coefficients of x3 in the rows above. So there's no rows below, but we want to do it in the rows above as well. So we can do this by saying row 2 is equal to row 2 minus 2 times row 3, and row 1 is equal to row 1 minus -1 times row 3. So this gives us the set of equations shown here. And you can see that we can now find each of these variables directly. So x1 is -3.5, x2 is 15, and x3 is -8.5. In matrix form, the steps are shown here. So you can go through kind of the same idea of what we did with the naive Gauss elimination and show how we arrive at this result. And you can see in the end, at our last step, our A is the identity matrix. So we don't need the backward substitution. We can get our X directly. So I also implemented the Gauss-Jordan elimination method in MATLAB, and where it prints out the matrix, the intermediate matrices, so you can see what's happening. And this is the result for the example that we looked at here. So that concludes the Gaussian elimination style methods for solving systems of linear equations.